In this lesson, we're going to talk about area. Summations in general you may have seen in previous classes. They're useful things to know. This is what we call sigma notation. Sigma notation is written with the Greek capital letter sigma. We've got this indexing variable I, and I ranges from 1 to n. And then you simply say, well, what does it look like? This is a function of I right here. But what it means is you plug in 1, then you plug in 2, then you plug in 3, and you go all the way up to n and add all of them together. We'll do a few examples of this. We call these things I is the index of summation. A sub I is the ith term. Again, that is a function that we're talking about. And then you've got upper and lower bounds of the summation. These words are just ones that you guys should recognize whenever I say them. Let's see if we can do these. For your first example, the function is just I. So when I plug in 1 for I get 1. When I plug in 2 for I get 2. When I plug in 3 for I get 3. And my upper bound is 4, so I'll stop there. When I plug in 4 for I get 4. So this summation is equal to 10. Next one. I is going from 0 to 3. So I'm going to plug in 0, 1, 2, and 3. When I plug in 0, let's write it like that. Then I'm going to plug in 1. Then I'm going to plug in 2. And then I'm going to plug in 3. So I'm going to go from 0 to 3. Let's see, I get 1 plus 2 plus 3 plus 4 again. Huh, how strange. Or is it? Next one. Now we don't necessarily have to use the letter I every time. We can use the letter J. So for this one, I'm going to go from 2 to 6. I get 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared. So let's just write all that down. I get 4 plus 9 plus 16 plus 25 plus 36. A little bit to add up. I get 90 out of that. Next one. So we're going to have 1 over the square root of k, and I'm just going to plug in 1, plug in 2, plug in 3, and plug in 4. You could simplify this a little bit, so I guess I'll start it. I get 1 plus 1 over the square root of 2, you can't do any better. 1 over the square root of 3, you're rather stuck with, and I do get a 1/2. So just to write a clean final answer, I get 3/2 plus 1 over the square root of 2 plus 1 over the square root of 3, and that's about as good as it's going to get. I would have been satisfied honestly right here, though, at the very beginning. Next one. So this one's a little bit strange, and then it goes from 1 to n. I'm just going to show you the pattern because I can't write it all down. And there's even a 1 over n here. Now that 1 over n does not have an I in it, so it's just going to sit there. So the first one is 1 over n times, well, 1 squared minus 1. Plug in 1 for I. Plus 1 over n times 2 squared minus 1. Just plug in 1 for I. Plus 1 over n times 3 squared minus 1. Plug in 3 for I, and so on. At the very end, you end up with 1 over n and n squared minus 1. You could clean this up a little bit, but at the end, you're going to run into some funky stuff in the middle that makes it too complicated. So I'll just leave it like that. Now, I will say you can come up with a few patterns. Like, there's a minus 1 that shows up n times. There's n of them, and it's multiplied by 1 over n, so I claim all this is just going to become minus 1. But the rest of it's a little bit harder, so I'm going to leave that be. Here's how we would actually handle this sort of problem. We've got some properties of summations, and I'm going to show you guys a little bit of examples of this. I'll talk about it a little bit, but I don't plan to talk a lot about it. Here's some properties of sums. First off, a summation can be split over plus or minus. You can take a sum of each individual part of the formula. Second, a k can be pulled in front. Any constant multiple, just like an integral, you can bring it in front. And so these are the little techniques that you can use. And you can make more of these. There's a formula for every power of I, but just to be able to do what we had earlier, here's some ideas. If you add up 1 n times, you get n. I think that's obvious. If you add up I n times, you get this interesting formula, and you might have even encountered this at some point if you ever heard the story of Gauss and adding the numbers from 1 to 100. Then there's I squared. I squared, if you add up all the sums, you get this formula. And I cubed, if you add them all up, you get this formula. Now with that said, this is a little bit tricky looking. I'm going to show you one example where these get used, but don't expect that you have to use these a lot. First example is we want to calculate this summation and evaluate it at 4 values of n and then take a limit. First thing I want to do with this summation is I've got I minus 1 over n squared. I'm going to start by just taking the 1 over n squared in front. And then I can break it up into 2 summations. I get I equals 1 to n of I minus the summation I equals 1 to n of 1. Now that's the cleanest breakdown I can do to it. So here's what I get. I got a formula for this one. I becomes n times n plus 1 over 2 when added up from 1 to n. And the summation of 1 was just n. So if we write that out, I'm going to write 1 over 2n squared times n squared plus n is what was in the numerator. Then 1 over n squared minus n would just be another 1 over n. So now let's distribute it again. Let's do some more of this. I get 1 over 2n squared times n squared is a half. Plus 1 over 2n squared times n is 1 over 2n minus 1 over n. So what I'm thinking of is this is like 1/2 of 1 over n, and this is just 1 of 1 over n. So my final answer is 1/2 minus 1 over 2n. That's what I claim to be the answer. Let's evaluate this at a few values. So if I plug in 10, I get 1/2 minus 1 over 20. I get 0.45. At n equals 100, I have 1/2 minus 1 over 200. And I get 0.495. At n equals 1,000, I get 1/2 minus 1 over 2,000, which is 0.4995. I see the pattern. N equals 10,000. I get 1/2 minus 1 over 20,000, which is 0.4995. So if you're looking at this, you might expect that the answer to the limit is going to be 0.5. It definitely appears to be traveling that way. So let's just take the limit as n approaches infinity of 1/2 minus 1 over 2n. Now it's been a little while since you took limits, but remember that a limit of a constant is the constant. And anytime there's an n in the denominator, the limit goes to 0. So sure enough, I get 1/2, and I will point out that's 0.5. Some of these actually end up with some numbers, which is kind of interesting. We're going to look at some areas by adding up rectangles. And it turns out when you do these rectangles, you always get sums that look a lot like what we had before. What we're going to do is I'm going to draw in some rectangles. Use 4 rectangles, it says, and we're looking at the interval from 0 to 2. I'm using a left endpoint with what I'm doing right now. I'll show you guys what I'm talking about in a second. Here's my 4 rectangles. These 4 rectangles are set with their height so that the left side matches up with the curve. That's my goal. This is what I'm going to call a left-hand sum. For the left-hand sum, we need to figure out, well, what is the area of those rectangles? Here's how I do it. It's going to be a summation. This is interval from 0 to 2. So we've got half as the length of our interval. So 1/2 is the width of the rectangle. And at 0, I'm plugging this into the function to get this. The height of the rectangle is 5. At 1/2, it's 5 minus 1/4. 1/2 times, I'll just write it as 4.75. We'll keep this as decimals to make this easier. At 1, I get 1/2 times 4. And at 3/2, I should get 2.75. That's how we set it up. The first rectangle has height 5 and width 1/2. The second rectangle has height 4.75 and width 1/2. The third rectangle has height 4 and width 1/2. And the last rectangle has height 2.75 and width 1/2. So if we add up all this stuff, I get 8.25 as my answer. So that's the sum of the areas of these 4 blue rectangles. Now, that's what we call a left-hand sum. Next, I'm going to consider the right-hand sum, which is made by doing the rectangles so that they align with their right end on the curve. Now it's a little bit different. For the right-hand sum, again, the height is a function value. The widths are still 1/2. The first one has the height of the second rectangle, what it used to be. So I get 4.75. The next one has a height of 4. The next one has a height of 2.75, just like this one was. And this one we'll have to calculate. It is at 2, where its y value is coming from. So if I plug 2 into here, I get 5 minus 4, which is 1. Putting this together, I get 6.25. If we want to approximate the area under the curve, what we're going to do is we're going to take a guess by taking the average of these two numbers. And I get 7.25 is going to be my best approximation for the area underneath this curve. And the approximation, by the way, is kind of like if I were to draw these diagonal lines in here. You'll notice that that follows the curve pretty closely. That would be the area underneath those diagonal lines. Pretty close, tiny bit too small, but pretty accurate. With that said, this is how we're going to define area, and this is why we did some summations. This looks complicated, and I'm not going to even do an example of showing you one of these in their generality right now. I'm just going to give you the idea of what we're doing here. If we have a continuous non-negative function, then we can find the area by taking the graph, the x-axis, and the two lines of our choosing, in this case 0 and 2, or it might be given to you in the problem. And we take the area by using this formula. It's a complicated looking formula. So let me explain it a little bit, and then we'll do it with pictures also. Delta x is the same kind of delta x that we talked about for derivatives. It is the change in x, and so this is the width of the rectangles. So we have b minus a is the length of the interval, divided by n splits the interval into even numbers with your n rectangles. xi is the x value that we're plugging in. These are right endpoints. What we do is we take I from 1 to n, and this increment will give it to us. So let me show that to you on the picture. So if I were to draw, I've got 8 rectangles this time. And these 8 rectangles, their area together represents the area under the curve. Delta x here is the width of the rectangle. b minus a over n, let's just mention this, would be 2 minus 0 over 8 rectangles. I get 1/4. And as you notice, that is the width of every rectangle. It is 1/4. xi would be 0 plus I times 1/4, which in this case is 1/4 I. Now I is going from 1 to 8 in this setup. So when I is 1, I'm looking at 1/4. When I is 2, I'm looking at 1/2. When I is 3, I'm looking at 3/4, and so on. This categorizes all the x values of the function all the way up to 1, and these are the x values of the right endpoints. where does the rest of the function come into play? F of xi is the height of the rectangle. Delta x is the width of the rectangle. So what we get is the area of the rectangle. It's the width times the height. We add up all the areas, and that gives us the sum of these like we were doing a minute ago. So where does this limit come into play? Note something, that this value, this set of rectangles, compared to the green ones I drew before, capture more of the area under the curve. If I were to double it again, I'd have even less error. Here's the idea. If I continue to add more and more rectangles, I get a better and better approximation. If I take the value as the limit of the number of rectangles goes to infinity, that is the area under the curve. I don't want to do a formal problem with this. This is just the idea of how to do these. And we'll talk more about area in the next section.